This is the final video for Math 1325 on Wednesday, August 17th. We're going to be doing the second half of the review for the final today, problems 16 through 30, and then you'll be all set to finish up homework and the review, and you got the next 2 days, Thursday, August 18th, Friday, August 19th, 2-day window to study, review, practice, and then take the final exam by Friday night. So we're going to move on to number 16 next. Find all x values of all points where the function has a relative extrema, and then find values of them. Okay, so they want the x values and the values, I mean the y coordinates. So we have a cubic function, x cubed minus 3x squared minus 24x plus 1. 3x squared minus 24x plus 1. So very similar to number 15, the way this is going to start is get your derivative of the original function and find all the critical numbers. So 3x squared minus 6x minus 24. Since this is a polynomial, this is never undefined, and it equals 0 possibly twice. Luckily, I can divide everything by 3 and make the numbers smaller and easier to factor. X squared minus 2x minus 8. Okay, so then we need one positive, one negative. It's either 8 and 1 or 4 and 2, but negative 4 and positive 2, that multiplies to negative 8, and 2 minus 4 is negative 2. So there are two critical numbers, negative 2 and positive 4. So those are the only two places over the whole infinite domain of polynomials where you could possibly have any local max or local min. And just because you get two critical numbers doesn't guarantee there will be two local extrema, but usually when we do these simpler problems with polynomials, usually they both are, but we wouldn't know that till we check, and we would have to see which one is which. So I would put on a number line, the smaller number on the left, bigger number on the right. Pick like negative 3, 0, and 5. Plug these into the derivative. And you can do it into the original derivative or even the reduced version, which is easier to work with. X squared minus 2x minus 8. And if we're using the first derivative test, then all we really care about is, are these answers positive or negative? So I'm going to use my test point of negative 3. Negative 3 squared is 9. Negative 3 times negative 2 is positive 6. 15 minus 8 is 7. This is positive. When a first derivative is positive, an original function is increasing over that interval. And it can't stop increasing and change to decreasing until you get to a critical number. So if your graph has no critical numbers, then whatever it's doing in one spot, it's doing everywhere. So this graph would be increasing forever unless there was a critical number, and once I get to that critical number, it's not a guarantee that it's going to switch, but it's going to be flat at that moment. And now I got to check the next test point. This will tell me if it's going to keep going up or if it's going to turn around and go down. So f prime of 0, that's easy, it's negative 8. So it did switch to negative, and therefore it's now decreasing at that spot. So that is a local maximum by the first derivative test. Our derivative switched from positive to negative at a critical number. That's a local maximum. So there's a local maximum at x equals negative 2. We don't know the y value of it, but we'll do that at the end. If you did use the second derivative test, which somebody could choose to do on a problem like this, even though it didn't ask you to do that, The second derivative test could have told you that it was a local maximum in one calculation, but this takes two calculations. You need to look at the derivative on each side of a critical number and see if the signs change. And then you do a similar thing when you get to the critical number of 4 by doing f prime of 5. If we want a local extrema there, we need the derivative to switch signs again. So f prime of 5, you'd get 5 squared is 25. 2 times 5 is 10, so minus 10 minus 8. But 25 minus 18 is 7 again. So again, it does take two calculations, although we're sharing the middle calculation. So we really just did 3 calculations, but we need to use 2 at a time. So I reuse the f prime of 0 along with f prime of 5, and that surrounds another critical number. So since the derivative switched from negative to positive there, it went from decreasing to that one point in time where it was flat, and then it increases after that. So this is a local minimum. So -2, that critical number is a local maximum. +4, that one is a local minimum. They said find the x values where the max and mins occur, and then also find the y values of them. So at this point, all we know is that x equals -2 and x equals 4. This is a local or relative maximum. This is a local minimum. Sometimes they only ask for that, but they wanted the y values too. But the key thing for that is you plug these critical numbers back into the original function. You don't plug them into the derivative function. In fact, if you did plug them in the derivative function, both answers would be 0, because that's why they were critical numbers. So we need f prime of -2. -2 cubed is -8. -2 squared is 4 times -3 is -12. -2 times -24 is +48 plus 1. 49 minus 20 is 29. And then if you plug 4 in, 4 cubed is 64. 4 squared 16 times -3 is -48. 4 times -24 is -96 plus 1. 64 minus 48 minus 96 plus 1, -79. And it's good that the local minimum had a smaller y value than the local maximum, because we only have 2 potential spots. So this graph is coming up, hitting the local maximum, then it goes down, hits the local minimum, then it goes back up forever again. And that's typical of an x cubed graph anyway. So this is the coordinate -2, 29. And this coordinate is 4, -79. In a section coming up, there's some problems where you graph using all this derivative information, and this is part of the graph is finding any local maxes or mins. That's really the calculus side of graphing those problems. Then there's a bunch of algebra side to it, like you can do the end behavior, you can find the zeros like we do in algebra, you can find the x and y intercepts, and adding all those points on there helps too. But right now I just need -2, 29 for the local maximum. There is one of each. Again, you're not guaranteed to get one of each, but we did get one of each. And they want the value first. There was a relative maximum of 29, that's the y value, at x equals -2. And then there was a minimum of -79 at x equals 4. Okay, so that was 16. 17 is when we learn the second derivative of a function, and then you could redo all this problem using the second derivative instead, which involves less total calculations involved, but it just confirms the same information. So I wouldn't redo 16 after I already did it with the first derivative test unless I just want to double check myself. So 4x to the 4th minus 2x cubed minus 2x squared plus 3. The first derivative is just the power rule. 4 times 4 is 16, and decrease the exponent by 1. 2 times 3 is 6, decrease the exponent by 1. 2 times 2 is 4, decrease the exponent by 1. There is no x term, first power, but the derivative of 3 is nothing. Then I can do the derivative of the derivative, which is a second derivative. 16 times 3 is 48. Decrease the exponent by 1. 6 times 2 is 12. Decrease the exponent by 1. The derivative of negative 4x is just negative 4 because that's linear. So this is the first answer they want. The second derivative function is 48x squared. 48x squared minus 12x minus 4. Then you can plug numbers into that, because that would tell you where the original graph is concave up or concave down, or if you get 0 for it, then you could possibly have an inflection point there. So 0 into this is easy because everything goes away except for the negative 4. Plug 4 in, I would need to do 48 times 4 squared. 4 squared is 16, so 48 times 16 minus 12 times 4 minus 4. 716. So if a second derivative is negative first, and then you get to a spot where the second derivative is 0 or undefined, and then you get a positive on the other side of that, that's an inflection point when that occurs. Although we haven't found the inflection point here because we didn't find when the second derivative is 0. But if it changed from negative 4 to positive 716 between 0 and 4, there must be an inflection point between those two, because the graph's switching from concave down to concave up. But that was just when you were learning how to find the second derivative first. So here in number 18, we kind of put everything together in one problem in order to help us draw a good sketch of a graph. So negative 4x cubed minus 12x squared plus 288x minus 12. So first derivative is negative 12x squared minus 24x plus 288. Polynomial is never undefined. It could equal 0 twice. Hopefully all this stuff divides by 12, and I'm even going to divide by negative 12 just to make the x squared term positive. And it's nice if you can get a positive 1x squared. That makes things easier. So negative 24 divided by negative 12 is positive 2. Hopefully 288 divides by 12. Whoops. Yes, 24 times, so that would be minus 24. So we need two numbers that multiply to negative 24. That means one's positive, one's negative. And then they got to subtract a positive 2, so positive 6 and negative 4. We have two critical numbers, negative 6 and positive 4. And I could do exactly what we did on number 16 and use the first derivative test and see if the derivative changes from positive to negative or negative to positive around each of these critical numbers. And that would show that there's local maxes and mins at them. But I can also do the second derivative test, which is usually less work. If you can get the second derivative quickly, then you may as well do that because that's less work. So whether I use negative 24x and negative 24, or I could have done 2x plus 2 would have given me the same answer. There's going to be one time that this equals 0 because it's never undefined. x equals -1. This is sort of like a critical number for the second derivative, but it doesn't really have a name. So what this is used for is I can make a number line around -1 and use -2 and 0, let's say. If I plug that into the second derivative, that'll tell me when the graph's concave up and concave down. So plug in -2, you would get positive 48 minus 24, that's 24. So the second derivative is positive all the way until you get to -1, and then when you plug 0 in, you just get -24. So there is an inflection point at x equals -1. That's mainly what the second derivative is used for. But if you go back to the first derivative critical numbers, instead of making a number line and checking is it positive or negative, positive or negative, positive or negative, that's 3 calculations. You can just do 2 calculations by plugging the critical numbers into the second derivative, not the first derivative. If they're immediately positive or negative, you can tell if there's a local maximum in there. Now, if there's 0, then it's inconclusive, but 4 times -24 is a big negative, minus 24, it's definitely negative there. So the second derivative is negative at 4. If you're a second derivative that's negative, that means you're concave down. And if you're doing so at a critical point where it's flat, it must be a local maximum. So I can tell this is a local maximum in one calculation. And I could have done it in 2 calculations if I would have picked test points on either side of this into the first derivative. So I'm just choosing to do it this way since I need information about the second derivative anyway. Plug -6 in. -6 times -24 is a big positive number, and then minus 24, it's not going to get it unpositive, so it'll stay positive. So if you're positive at a critical point, if you have a positive second derivative, that means you're concave up, and if you're doing it at a critical number, then it's got to have a local minimum there. So I determined both of those in 1 calculation each instead of 2 calculations each, which is really a total of 3 calculations. Okay, so that means I know 3 things. I know that there's a local minimum at -6, there's a local maximum at 4, and there's an inflection point at -1. And then I can get the y value of all 3 of those. And since the original function has large values, I would just put it in here. I'm going to do f of -6, f of -1, and f of 4 to get the y value of these 3 things. And we're plugging this into the original function. So -4 times -6 to the 3rd power minus 12 times -6 squared plus 288 times -6 minus 12. This is supposed to be a local minimum of -1308. Then if I repeat that for -1, -308 is the inflection point, the y value of the inflection point, and then finally do it for 4. This is supposed to be the local maximum, 692. So these 3 points were all determined from calculus knowledge. Then I can use college algebra knowledge. If you have a negative leading coefficient and an odd degree, the end behavior of that is it rises on the left and it falls on the right. And then we could certainly do the y-intercept real quickly. The y-intercept is definitely 0, -12. The x-intercepts wouldn't be so easy to find, but we can use college algebra knowledge to do that. And that could take another 15 or 20 minutes. So if we really cared about a lot of detail of the graph, we could do that. But we already have 4 good points that are on this graph. There's -6, with negative 1308. That's a little hard to graph, but we can just estimate it. That is our local minimum. We hit the minimum first this time. Local minimum. Then the next special point we hit is -1 with negative 308. That's an inflection point. That's a spot where the graph changes from concave up to down or vice versa. Now, local minimum, local maximum, they have separate names, but inflection point is one name for both possible ways it could happen. Then for sure, 0, -12, that's an easy y-intercept. And polynomials only ever have one y-intercept. They can't have more than one. This graph could have 3 x-intercepts because it's got a degree of 3. And then finally, 4 and 692. 4 and 692, that's the local maximum. And the end behavior, in college algebra, we would just tell students, okay, the end behavior is rises on the left, falls on the right. And they would bend it down and cross the x-axis 3 times. And then we would just tell them, okay, when you get to a spot, just after you cross an x-intercept, just turn around at some point and go to the next one. But now, with calculus knowledge, you can know where it does turn around. So if I put the rises on the left end behavior, then I would want to get to -6, -1308. So without taking time to find the first x-intercept, it clearly is going to happen before -6, because I have to, by the time I hit this local minimum and turn around, that's the coordinate -6, -1308, or whatever that y value was. So this will be like -7, -8, -9, maybe -20. It might not even be an exact number either. So there's the local minimum. And this entire portion of the graph is concave up so far. It's still bending in an upward fashion until we get to -1 and -308. Something like that. There's -1, -308. Let me do this a little better now that I know where I'm going. Because we do have to hit 0, -12 also. So here's 0, -12. Here's, let me just put it on here, -1 and -308. And then down here somewhere is -6, -1308 or 9, whatever it was. They're both 8s. Okay, 1308. So from this point right here, all the way through the local minimum and to infinity, that's concave up right there. So I've got an upward curvature this way. And then the local maximum is 4 and 692. Let's just put that here, let's say. 4 and 692. So it's concave up from -infinity till you get to -1. There's the inflection point. Then it's concave down the rest of the time. So now the curvature bends the other way through there like that. So it's concave down all the way to -1 on this side and concave up on -infinity to -1. This spot right there is when it switches from concave up to concave down, which college algebra students don't know that. And then I go through my y-intercept, and then there can be 1, 2, 3 x-intercepts, and if I really cared where they were exactly, then I would spend more time doing college algebra knowledge where you go find all the zeros, like using the list of rational zeros, and then use your Descartes rule of signs maybe, and you can look for lower and upper bound theorem can help. And then you just guess and check till you find the first zero using synthetic division. And so you could spend another 10 or 15 minutes doing all that. But luckily this is multiple choice, I have enough to be able to tell. It's definitely not graph C or D. And then this looks wrong because it's supposed to, well, they both look like they're going through the origin. So it's just because the scale is so large. It looks like it's going through the origin, but that's really 0, -12 on both of them. They just can't show that much detail when it goes all the way down to -1500. But we did know the local minimum was like -1308. So that looks closer to -1308 than this is way too short. That's not even halfway to -1500. And then remember, the local maximum was 600 and something. So that could be 600 right there. Or that's clearly not 600. That's probably not even 100 right there. So the graph's definitely B. And then I have my local minimum at -6, -1308. It's a little hard to tell when this curvature changes from concave up to concave down, but we know it's happening at -1, -1 and -300 and something. And then at 0, -12 is the y-intercept. So that means the second x-intercept is some positive value. There's a negative x-intercept here that's after -15. Then there's one that's slightly after 0, and it might be some uneven spot too. And then there's something between 0 and 15 over here. But since it's just multiple choice, we don't really care about that. But we could combine our college algebra knowledge with calculus knowledge and get even more information there if we needed to. Okay, the final thing of this chapter was you can find, we talk a lot about local max and local mins a couple of different times, both with the first and second derivative test. They're very special points. But then we're also sometimes interested in absolute maxes or mins. And if you just have a graph like a line, it goes up and down forever. It doesn't have a absolute max or min. So many graphs don't have an absolute max or min because they're unbounded and they go up and down forever, or at least one way forever. So one way to get absolute extrema is to put a closed interval on your function. If there's a closed interval, then you're guaranteed to get an absolute max and an absolute min, and they occur at either the endpoints or any critical numbers inside the interval that's given to you. So number 19, the original function is fourth power, x to the fourth minus 72x squared plus 1, and we're going from -7 to 7. There could be 3 critical numbers to this entire function, because the derivative is 4x to the third minus 144x, which can never be undefined, but it could be 0 3 times. And if I divide by 4, that could make things smaller and easier to deal with. 72.5 is 36. This has a GCF of x, and that's a difference of squares, x plus 6 and x minus 6. So I have 3 total critical numbers, 0, -6, and +6. But -6, oh no, it is, okay. I was thinking it wasn't in the interval, but it goes from 7 to -7. But if this had been -5 to +5, then 0 would be the only critical number in that range, and we could cross out the 6's. But we don't get any shortcut here. We got 3 critical numbers that are all inside the interval, so we're going to have to make a list of x's that come from endpoints and critical numbers. And then if we plug them back into the original function, whichever one of these is highest or tied for the highest and lowest and tied for the lowest, these will be the absolute max and mins. So I need to do -7 to the fourth minus 72 times -7 squared plus 1 That is negative 1126. Second enter, change all the negative 7s to negative 6s. Now we're negative 1295, that's even smaller. So negative 7 is not the absolute minimum, that's all we know so far. 0 is easy, you're just going to get 1 for the answer to that. Then change your negative 6s to positive 6s, delete the negatives. Negative 1295, we got a tie so far. And then change the 6s to 7s. Negative 1126. So the absolute maximum in this interval is when the y value is 1, and that occurs at x equals 0. So there's an absolute maximum of 1 at x equals 0, and then there's an absolute minimum of negative 1295 that only occurs once at both 6 and negative 6. So the values only occur once if you're guaranteed to get them. So we have both an absolute maximum and an absolute minimum. There's an absolute maximum of 1 that occurred at 0. There's an absolute minimum of negative 1295. It occurred at both negative 6 and positive 6. So there can be a tie for the location. And that's what we do with a closed interval. If you get an open interval or a infinite interval, or even a closed interval, if it's any interval and it turns out there's only one critical number in it, if that one critical number turns out to be a local max or min, then by default it's also an absolute max or min. So that's more important when you have an open interval or an infinite interval. Then your only hope is to have just one critical number. Okay, then we did what's called implicit differentiation. When there's more than one variable going on, that's not just y, for example. So I have 2x cubed equals 7y squared plus 9y. So I have both x's and y's, and it's not just simply y equals. Up until this point, they always just gave you y equals. They would never give you other complicated y parts. So, and technically you were doing this when it was just y equals, it just the derivative of y is 1, and it kind of got ignored back there. But you're just going to do each term or each rule as you go across. You might see like chain rules or quotient rules or product rules could happen too. But this is just a term by term one. So I'm going to do the derivative of each term. 2 times 3 is 6. X to the decrease that by 1, that's a 3 to a 2. Then you do the power rule on this y as if it was an x, and you do 7 times 2, 14, y to the first. But since you did it to a y variable, then a dy over dx happens as well. That's kind of like the chain rule part of that. And the derivative of 9y is just 9, but then chain rule times the derivative of y, which is dy over dx. So if you do x, you just do it normally. If you do y, you just attach a dy over dx each time you have a y part. And then the goal is to solve for dy over dx. And you end up not caring how messy the other side of the equation gets. So I would factor out the dy over dx on this side. Sometimes you have to move terms across the equal sign to get all the dy over dx's on one side and all the non-ones on the other side. But here we got lucky that all the terms with dy over dx were on the same side of the equation. Divide by everything but the dy over dx. And you usually get a fraction that can be messy and complicated, but we don't really care. This fraction will have x's and y's in it. So dy over dx equals this. Or we could later multiply both sides by dx as well. And that's kind of getting you ready for integrals, antiderivatives, where one side's all about y and the other side's all about x. But here they actually want dy over dx, so we don't multiply both sides by dx. See, dy over dx equals, so the top of the fraction was 6x squared, and the denominator was 14y plus 9. Okay, so that's what happens on this one. First, you're going to do the same thing as 20. Y equals 2x cubed minus 7x. So the derivative of y is 1 times dy over dx, or as we learned when we first learned derivatives, the one symbol for saying I'm doing the derivative of y is to say dy over dx. And then this side would be 6x squared minus 7. That's how problem number 20 went, except we had to do some algebra after that. But here, the extra step is then you multiply both sides by dx. So 6x squared minus 7 dx. If you were to do an integral of each side, that's where the integral of dy would just be y. And then this, you would do your antiderivative rules over here, and then that would get you to an antiderivative. That's why you always see that dx in the antiderivatives problems. But what we're not doing an antiderivative here. They're telling me that x is negative 3, and delta x, which really is dx, that's the change in x equals negative 3, and delta x equals 0.2. So this goes in for dx, and this goes in for x, and then we can get a numerical answer rounded to the 10th or whatever they say. So 6 times negative 3 squared minus 7 times 0.2. Negative 3 squared is 9, times 6 is 54. 54 minus 7 is 47 times 0.2. And it does say round to the nearest 10th. 47 times 0.2 is 9.4. There's not even a need to round. It came out exactly to 9.4. So if you change an x by a value of 0.2, like say you move from negative 3 to negative 2.8, if you increase the x from negative 3 to negative 2.8, which changes it by 0.2, then the y would change by 9.4 when you do that. That's what the dy is representing, the change in y for a given value, for a given change in x. So that was the end of derivatives right there, 21. So now we're into the final chapter where we're doing antiderivatives. The integral of 10 fifth root of x, I'm going to rewrite the fifth root of x as x to the 1/5 power. It's always good to work with fractional exponents over radicals, whether you're doing derivatives or antiderivatives. And they actually wrote this one as a fractional exponent, minus 8x to the 1/7. Okay, this is the power rule for antiderivatives. You first write your 10x, then you increase the exponent by 1 instead of decreasing it by 1. 1/5 plus 5/5 is 6/5, and then you divide by that new exponent. Move to the next term, minus 8x, increase that by 1. 1/7 plus 7/7 is 8/7. Divide by 8/7. If it's a indefinite integral with no numbers here, then you just put a plus c at the end. And then you can flip the second and multiply on these two denominators since they're fractions. That would cancel all this out. Flip the second and multiply here. So 10 can go into 6 twice. 10 divided by 2 is 5. 6 divided by 2 is 3. So we're left with 25 over 3. x to the 6/5 minus, here we get lucky that the h's outright cancel, minus 7 x to the 8/7 plus c. And yes, you could change them back to radicals, but they take the answers this way too. So some people say make the answer look the way it did in the original, and they would leave this one as a fractional exponent and they would change this to a radical again, but we don't have to. So 25/3 x to the 6/5 minus 7x to the 8/7 plus c. Okay, then we have to use substitutions is the next thing we learned in section 7.2. So generally this reviews kind of has one problem from every section we did. Some have a couple of problems if there's two main topics in a section, but one or two problems from each section. So integral of 8 x to the 7th. And then we got e raised to an exponential part, e raised to the 4x to the 8th. So the x to the 8th part, that's going to be my u, what I set equal to u, because I know the derivative of an 8th power drops down to a 7th power. And what do you know? There's a 7th power right here. So du would equal 32 x to the 7th dx, using the power rule. Now we don't have a 32 here, we only have an 8, but if you're off by a constant, you can adjust. I wish that there was a times 4 right there, so that way 4 times 8 would give me the 32 that I need. But I can't just put a 4 there because I need it, unless I balance it with a 1/4. Putting a 1/4 and a 4 at the same time is putting 1, and that doesn't change the value of the problem. But the 1/4 will stay as a constant outside. Then I'm going to have e to the u, since the exponent was the u part. And then the 32x to the 7th plus the dx, that's what turns into du. And derivatives and antiderivatives of e to the u is easy to do. That's the one where it equals itself. The derivative or the antiderivative of just e to the u, when there's just a simple exponent like u, it's itself, which is exactly why we do this, is we try to make it an easy antiderivative to do. And then the final answer can't have u in it, so we got to go back and plug what u was equal to. It was equal to 4x to the 8th. So then I back substitute and put 4x to the 8th back in for u. And remember, if you took the derivative of this is itself times the derivative of the exponent. The derivative of the exponent is 32x to the 7th. And then the 32 times the 4th would get you back to the 8 that you originally had. So 1/4 e to the 4x to the 8th plus c. 1/4 e to the 4x to the 8th plus c. Okay, then before we learn definite integrals, the concept of definite integrals comes from these getting areas of rectangles. And then if you increase the number of segments that you want to have, I'm going to have 4 segments here. If you increase that larger and larger and larger, then you get closer and closer to a definite integral. So I have the linear function 2x plus 4. I want to have 4 rectangles. And I need to go from x equals 2 to x equals 4. So if you do 4 minus 2, the two endpoints, over the number of rectangles you want, That's the width of each rectangle. I need 4 rectangles that have a width of 0.5. So let me go half, 1, 1.5, 2, 2.5, 3, 3.5, 4. So we're going to have these 4 half width rectangles. And then if I figure out, we're going to need to know all 5 of these anyway, so I'm going to figure out f of 2, f of 2.5, f of 3, f of 3.5, and f of 4. Just, we can really put this on a graph too, but the y-intercept is 4. And then if you go up 2 over 1 repeatedly, then you'll have your line here. If I plug 2 in, 2 times 2 is 4, 4 plus 4 is 8. So 5, 6, 7, 8. 2, 8, that's a point on the line. And it would go all the way back through 4 right here. The whole line looks like this. But right when I get to that spot, that's where things are happening. So if I plug in 3, 6 plus 4 is 10, so 9, 10, 11, 12. Since it's linear, it's a little easier to know the next ones. So this is the entire line, not the entire line, but there's the part I care about. There's the entire line. So right here, I'm going to make 4 rectangles. And they all have half width. The width on each one is a half. The length on each one is the height, depending if you want to go from the left, the right, or the midpoint. So first what we do is we do left endpoints. And the width is 0.5 every time. So I need to do f of 2 plus f of 2.5 plus f of 3 plus f of 3.5. Those 4. Those are the 4 left endpoints. We're at 2, we're at 2.5, we're at 3, we're at 3.5. Then when you do the right endpoints, the only thing that changes is you start at f of 2.5 instead of 2, and you're going to get the 3 and the 3.5 still. But then you go all the way to the right, which is f of 4. And f of 2 was 8. 4 plus 4 is 8. F of 2 is 8. F of 3 was 10. And f of 4 was 12. I know that because I put those spots on my graph. But you can calculate them each time. Plug in a 2, plug in a 3, plug in a 4. F of 2.5 would be 2 times 2.5, plus 4. So f of 2.5 is 9. This one is 10. F of 3.5, it's going to be 11, but 2 times 3.5 plus 4 is 11. So add this up and multiply by a half, because really each one's getting multiplied by a half. But if you factor the half out, you can do that at the end. So the left summation will be 8 plus 9 plus 10 plus 11, and then multiply by a half or divide by 2. So the left, doing left rectangles tells me the total area of the 4 rectangles would be 19. For the right, I just have to do 9 plus 10 plus 11 plus 12 and cut that in half, 21. The average of these two, halfway between 19 and 21, is 20. But if it wasn't that easy, then you would add them up and divide by 2. And then for linear ones, it turns out the midpoint is the same as the average of those two, but that's not always the case if you don't have linear. But to do the midpoint spots, you would be halfway between 2 and 2.5, which would be 2.25. And halfway between 2.5 and 3 is 2.75. Halfway between 3 and 3.5 is 3.25. And halfway between 3.5 and 4 is 3.75. So the midpoint, using midpoints for your rectangles for the heights, for the lengths, you're still going to have half width intervals once you determine that it's the same in every version. But I need to do f of 2.25, f of 2.75, f of 3.25, and f of 3.75. Oops, went off the screen there. Okay, so I know what it is. So it's 2 times whatever x you've got plus 4. That's the function, 2x plus 4. So 2 times 2.25 plus 4 is 8.5. 2 times 2.75 plus 4 is 9.5. And as soon as you see a pattern starting, since this is linear, it's obviously going to continue. So 10.5 and 11.5. So add that up. Times a half or divided by 2, and there's the 20 that I knew was going to happen, but normally you wouldn't know that ahead of time. So the midpoint usually gives you the best approximation. And then if it's linear, the average of the left and the right will turn out to be the same as the midpoint. Is that why they make you do that? But if it's not linear, they usually don't ask for the average, and then you just do left, right, midpoint, or in many cases you would just do one of the three, but they're just trying to teach you how this works at first. So that's where the basis of the antiderivatives comes from. Integrals, definite integrals, is just having, if the dx, if that x is so tiny, instead of being 0.5, if that was 0.05 or 0.005 or 0.00005, as that gets tinier and tinier, then you can do an integral instead of doing all these sums of rectangles. Then it approximates it. So 25 is the definite integral from 0 to 5 and it's 5x squared minus 6x plus 4. So we do a definite integral. We start off the same way as an indefinite integral and do the antiderivatives. 5x, increase the exponent by 1, divide by that same exponent. 6x, increase the exponent by 1, divide by that same exponent. And a constant turns into a linear the same way a linear turns into a constant when you're doing derivatives. And then instead of putting plus c at the end, you evaluate this from 0 to 5. And I could simplify this down to a 3. So big F of 5 minus big F of 0, that's the fundamental theorem of calculus. That if I just evaluate this from 0 to 5, I get the same answer that I would if I did a bunch of rectangles added together. Especially if I had many different rectangles, a very large number of rectangles, and a very tiny width on each one. So 5/3 times 5 cubed minus 3 times 5 squared plus 4 times 5, that whole part right there, that's f of 5. And then you're supposed to do minus f of 0, but all three of those terms are going to be 0 since you're plugging 0 in for x each time. So it's nice when f of 0 gives you all zeros. It doesn't always, like if you have e to something. If my function was exponential e to the x, then I don't get all zeros here, but oftentimes you get all zeros when you do f of 0, big F of 0. So 5/3 times 5 cubed minus 3 times 5 squared plus 4 times 5. And they usually don't like decimal answers, so math, enter, enter. There's 460 over 3. Technically minus 0, but then that's going to be the same answer then. So 153.3 is the approximation. So if you drew this curve, this quadratic, and it would go above the x-axis the whole time, and then from 0 to 5, so you got some kind of quadratic from 0 to 5, the amount of area in under this curve and above the x-axis, it's entirely above the x-axis, that would equal about 153.3 is what that's saying. So 460 over 3. Okay, then what happens is that first 125, that one was entirely above the x-axis. But now you might get it where part is above and part is below. So when that occurs, then you got to break it up into two different integrals, or possibly more than two if it happened more than once. So my original function is 8 minus 2x squared. And I want to go from 0 to 7. This is a quadratic, and it has a starting value of 8. It's an upside down parabola, vertical stretch of 2. So 40, I didn't draw this well because it's going to be mostly negative actually. When x is 2, 2 squared is 4, times 2 is 8, that's when it hits the x-axis at 2. So actually I need to draw it more like this. It starts here at 0, 8. It hits the x-axis at 2, 0. And then it just goes down in a parabola shape after that. So if I call this 7, just because I'm running out of room here, we've got a smaller area above the x-axis and a bigger area below the x-axis. So this is definitely going to have, if you just did an integral from 0 to 7, you would get a negative answer actually. The definite integral from 0 to 7 of this function would be negative because there's more area below the x-axis than above it. But if you actually are asked to find area, find the area, then we don't take negative portions. So then we have to do two integrals. We have to do an integral from 0 to 2 of your function, and that'll come out positively. Then we do another integral from 2 to 7 that'll come out negatively, but we can just flip the negative to a positive if we care about area. If you don't care about area, then you don't flip it. So my original function is 8 minus 2x squared. The integral from 0 to 2 of 8 minus 2x squared, that would be 8x minus 2x to the third over 3. And big F of 2 minus big F of 0. Big F of 0 is going to be 0 because I'll put zeros in for both x's. So the big F of 2 is 16 minus 2 to the third is 8 times 2 is 16 over 3. 16 is 48 over 3, so that's 32 over 3. But if you didn't know that, 16 minus 16 over 3, math, enter, enter, 32 over 3. That's how much area there is right up there. The area of the top portion is positive 32 over 3, obviously. When I redo this from 2 to 7, this is different than those problems where you're doing area between curves. So the antiderivative here doesn't change. It's 8x minus 2x. That's what I messed up on that problem number 5, is I was thinking of this kind of problem where it doesn't change. But in those problems, it does change, flips to the opposite. So now I need big F of 7 minus big F of 2. And big F of 2 is this 32 over 3 that we got. But in those other problems, it actually becomes minus a negative 32 over 3. And then big F of 7 would be 56, 8 times 7, minus 7 cubed is 343, times 2 is 686 over 3. 686 over 3. So 56 minus 686 over 3. Math, enter, enter. See, this is negative 518 over 3. Minus 32 over 3 is negative 183.333. Math, enter, enter. This is negative 550 over 3, which is negative 183. So this was a little more than positive 10 here, and this is negative 183. So there's a lot more negative area than positive area, but area can't be negative, so we just change that to positive 550 over 3. 550 over 3 is the total area below the x-axis if you just care about area. So 550 over 3 plus the 32 over 3 gives you exactly 194 total area if you care about area, like a geometrical size area. But as soon as oh no, this is the same thing. I was thinking of the next problem. So same deal, find the area of the shaded region. This area is going to turn out to be negative when I do an integral of it, but then I can switch it to positive to add it to the other one. So this is a very similar problem. They drew the picture for me as the difference. Is this 27 or 28? This is 27. So I need to do an integral from 0 to 3 for the function 9 minus x squared. This will have a positive answer to it. 9x minus x to the third over 3. Big F of 3 minus big F of 0. Big F of 0 is 0. Putting zeros in both of these will give me all zeros. So I'm going to get 27 minus 27 over 3, which is 9. So that came out evenly. 27 over 3 is 9. So that's 18. Minus 0 is 18. So this has an area of positive 18 right here. And clearly this doesn't have as much area as that does. So it's going to be a negative something, but it should be negative less than 18. So then I need to go from 3 to 4, not to 5, but 3 to 4 and do the same thing. If I go from 3 to 4, this will turn out to have a negative answer because I can tell from the graph that this is below the x-axis. This will have a negative answer, and then if I care about area, then I switch it to positive. So same antiderivative. The reason that antiderivative is the same is I didn't change anything about these two. But in the area between two curves, you do change these two. So that's why here I can do big F of 4 minus big F of 3. And I don't have to recalculate big F of 3, it's 18. It's just going to turn out to be minus that. Big F of 4 would be 9 times 4, 36. 4 cubed is 64 over 3. That doesn't divide evenly. So 36 minus 64 over 3. Math, enter, enter. That's 44 over 3. Minus 18. And this is why it's going to be negative. It's negative 3.333. Repeating. Math, enter, enter. That's negative 10 over 3. So the positive area is positive 18. The negative area is about negative 3. But then if I care about total area, and I'm talking area, then then I switch that to a positive. So 18 plus 10 over 3, 18 plus 10 over 3, math enter, enter, is 64 over 3. The total area is 64 over 3. And my battery's running low. Give me a second. Okay. Doesn't reach. Okay.